Sorry, now you can hear, I think. So I will repeat the thing I told. So I told earlier that giving so when you analyze a model, given the geometry, so doing the CAD model is not really uh, uncertain. So you can model a geometry, and when it comes to material selection, you have to think a little bit what to select as the correct material. So when it comes to loading, you have to think more what are the loads we are going to apply. So when it comes to restraints, that is constraints, fixtures, you have to think more than all these things. So there's a very big uncertainty behind this. So geometry is not a difficulty to model. Material selection, you have to think a little bit more. Loads, you have to think what are the load types I may get, and this is the most important thing. What are the what are the restraints? That is, connections and fixtures are really important when it comes to simulations. So in this model, this is not a difficult model, but when it comes to a complex shape, you have to carefully think about the connections. What are the, whether I have springs, whether I have pin joints, whether I have ball joints, whether I have bearings. Likewise, what are the fixtures I have to use? When shall I go with elastic support, hinges, roller sliders? So uh, think you have to think a little bit more than the others, and that's what it describes here. Giving restraints is the most difficult thing in SolidWorks simulation or any other simulation package. So we will start with a simple mesh now. So we will run three simulations and see how the results are changing. So we will start with the coarse mesh, and we will start go with the medium size mesh, and we will fine tune the mesh and see whether the results are going to change. So now I have given fixtures here, loads here. Now now we have to give we have to apply a mesh. So I will right click on this, and if you just click mesh and run, software will automatically uh, put a mesh and he will run the result and show. But this should not be done if you are not familiar with the software. So we will look at the theory behind this first, and we will click on the button called create mesh. So when you click on the button called create mesh, by default we are getting this kind of a slider. So the mesh size is in the middle at the moment. So if you look at these mesh parameters, the mesh, this is a standard mesh. That is, this is using first order equations, first order differential equations. This is a solid thing. So the software will use first order tetrahedral elements. So I will go back to the slides. We will use this solid element first order tetrahedral. So you can see curvature based mesh. Curvature means second order, and we have another one called blended curvature base. So when it comes to these second and third options, you are getting more settings, more fine-tuned shapes. So first one is the standard first order mesh, and it says some value is given 5.721, something like that. So this is the size of the element, and this is the tolerance of the element. That is, it can have plus minus difference between, because every element will not fit, especially in these edges, in these corners. This full element will not, may not be fit, so it should have a tolerance. And what do you mean by 5.7 is the size of the element. So if you just look at in a picture, this is the tetrahedral element. If you put this inside a sphere, the sphere diameter is the size of the element. So when it comes to a 2D shape, this is the diameter of the sphere, circle. So sphere diameter is the size of the element here, 5.7 tetrahedral element size. And if you just put this into course level details, this becomes double the value, 11.4. So in the middle it's 5.7. So this value is calculated by the software depending on the model size. So in your computer, you may have a slightly different value or exact value. So depends on the computer and the solving methods. This may change a little bit, and your results may not be exactly as my results because these are numerical techniques. So approximate answers will be given. And if you go to the fine values, this is the half of the medium value. So when you reset, it's 5.7. When you go to fine values, it's 2.8. So your tolerance is also getting reduced. So we will start, we will not go through the other settings at the moment. We will start with this basic course level detail mesh and 11.1. So this element is now very big, 11.1. So if you want, you can type your element size here. And element is measured in millimeters. And if I press OK now in the course level detail, it will put a mesh. So this is the tetrahedral element size, 11.7. If you look at the boundary here, it tries to match the curvature. Okay, and now this is the mesh. So if you just right click on this and get the details, now I can right click on this one and get the details. So it will show me the mesh details. So it's a standard mesh. Automatic transition is off. Jacobian points for. I will describe these things later. We have discussed this element size and tolerance. So this value is important. And mesh quality software has decided it's a high quality mesh. So you have to check whether the mesh quality is high or low. Should be high. And total nodes 2779. That is, it has 2779 vertices here. Those nodes. How many elements? 1400. So in your machine, this may be a little bit changed. You may not get exact values because these are numerical approximation. And aspect ratio. What do you mean by aspect ratio? Aspect ratio is I don't have a diagram. I will use the internet and show you what is meant by aspect ratio. So aspect ratio in simulation means the length to width ratio. Ratio between the longest edge and the shortest normal drop from vertex to the opposite face normalized with respect to a perfect tetrahedron. Perfect tetrahedral aspect ratio is 1. So if you just look at the diagram, so aspect ratio is this value. So if you look at this one, this is the aspect ratio, long edge length divided by short edge length. So if the aspect ratio is very high, that means your element is not exactly looks like a tetrahedron. If the aspect ratio is close to 1, that is your element is quite good in shape. So you have to have that tetrahedral shape correctly. That is, if you look at my mesh details, my aspect ratio is 6.61. So this is not really a good value. So if you just see percentages of elements with aspect ratio less than 3 is 98. So more than 10, 0. Distortion is 0. So this mesh is quite okay for this example because lot of elements are under 3. 98% is under 3. If you are getting something like say 10% here, more than 10 aspect ratio is around 15% of elements, that mesh is not a good mesh. So this is a criteria to check. Lot of elements should be less than 3. That is, it will maintain this original element shape, not the distorted shape. So I hope you understood it. So this is a high aspect ratio element. This is a good one. So it's perfect. Okay. So this is about triangles. Earlier one I is about tetrahedrons. So I hope you understood. So you have to look at those parameters. So the software will just give the values. I have to check whether this is good, whether I have a high quality mesh. Those things should be checked. Then now if the mesh is okay, and these are changes in the symbols. If you look at before meshing, this diagram is not hatched. Now after you mesh it, you can see some lines here. So the model changes. Now I have a grid here, a grid here. Before meshing, these are not grids. These are just plain symbols. So you can quickly see whether I have done a mesh or not by looking at these symbols. Now we will run it and see. Any questions up to this point? So I have applied a fixture, load, and a mesh. So mesh is, if you want to change the mesh, you can always go and click on the create mesh again. I have applied a coarse mesh. Other settings I didn't change. Then we will run it and see. Run the simulation. It will take some time depending on the computer, depending on the meshes. Now when I apply the run, it will show me the von Mises results. It will show me the yield strength 2.48. So this value is in megapascals. So I have shown you how to change this to megapascals earlier. We can go to simulations options. Under default options, we have this megapascal value. Default option megapascal. So that's why you got megapascal. And you can see the model has been distorted. And if you want, these can be represented by, this is scientific value. So you can change it to normal floating numbers. So we can right click on this and go to edit definition. We can right click on the plot and go to edit definitions. Here under advanced options, under chart options, we have this scientific thing. Under chart options, we can change it to floating. So when you change it to floating, you can see the numbers are easy to read, and decimal places 3. Okay. So I got my von Mises results, and yield strength is shown as 248 here. This is a ductile material, and the maximum value is 343. That is, I am going beyond the yield strength. That is, these areas are failing. So if you look at these red color areas, this design will permanently deform. So when you apply 100,000 newtons, these areas will permanently deform. The blue areas are okay. So that's my conclusion. So I have to make sure these results will not going to be red. So how can I do that? We will look at that later. So I hope you got the results now. Everyone should get a value closer to 343. You may get 340, 345, depending on the computer. And this is actually a scaled up model. Deformation scale is 161 times enlarged. So this is just to show you the changes. Otherwise, this is not the very actual change. It's a zoom in 161 times. So if you look at the displacement plot, these are the maximum values we get. So this area we are not displaced because it's fixed. Red areas are going to be displaced by 1.23 millimeters, 0.123. So if you right click and go to definitions here, we can change the scientific value to plot in numbers. So you can see this is the change. This is cast carbon steel. I have applied 100,000 newtons. Only 0.12 millimeters we are going to change. But you can see there's a big change in the uh, plot because I have enlarged this by 161 times. If you try to animate this, right click and there's a tool called animate. This will change a lot. So this is actually deceiving your eyes because this is 161 times enlarged. So you are actually changing 1.1 millimeters. So this is the animated result. So you can save it as a AVI file if you like. I will close this. Stress plot also you can right click and animate. But this is not the actual scale. So if I want to get the actual scale, you can right click on the scale here. Sorry. Right click here or go to edit definition here. So from here also I can go to edit definition. Then we can go to true scale or 1:1 scale. So if you go to true scale, this is the change. So you may not see a change. True scale, I can't see a change, a great change. Actually, it's not changing. So to show you the results, they have enlarged the scale. This is the actual case. So if you look at the displacements, and if you go and change it to true scale here and animate it, you cannot see a deformation. It's 0.124. That's why they have enlarged that area. Now I can see a change. Okay. So when you give this results to a person, you have to inform that reader that this is 161 times enlarged. This deformation has been changed, enlarged by 161 times. So when we can generate a report, in the report it will mention that. And when it comes to strains, these are the results of strains values. Normally we care about the stress because we have to get the factor of safety. These values should be compared. So my design is having problems in these red color areas. Now if you want to show the maximum point, you can right click here and go to edit definitions, and under chart options we can show the maximum value and minimum value also. So these are the two values we are getting. So if you want, you can remove this legend. A lot of things are there. We will discuss them later in while. Color variations we can give. Then we can go to, we can plot a different parameter here even. Then under advanced options, we can show the element value if you like. Element value, if you press OK, this is the result. So it's not a continuous plot. So you can right click and go to advanced options and show the node values. Node values are more continuous. Then we have chart options, maximum, minimum, plotting numbers. Okay. Any questions up to this? So I will save my model. And when you look at your folder now, you will see a lot of files have been created. So I started with this one. I didn't create any of these files. So that's why we should have this in a folder and do the work. Otherwise, there will be 10 or 20 files created, and you will get a lot of files in the desktop. So better you create a folder and do this. So these are internal files created by the software. So you are able to generate the result like this. So any questions about this stress, displacements, and strains? So after you get the results, don't believe this. So this all this depends on the loading conditions you gave, the fixtures, and especially the mesh. So I have given a coarse mesh. Is this result is a valid result? So we have to think about that. We have to rerun the simulations several times and get the optimum value. So after we get the optimum value, only we have to change the design. So this area is red. We have to do some material adding. No, we have to say apply some fillets and try to just reduce the stresses in those areas. So those are later operations. First, we have to get that most accurate stress and displacement values. Any questions about this before we moving on to the next one? So we have to now, if you want, you can plot the factor of safety graph also. So if you want, you can get the FOS plot. So factor of safety, we can ask the software to generate always by right clicking and adding a new plot here. Then he will generate every time when we run a static plot. He will static study. He will generate, but we may not need factor of safety every time because we can just look at these two values and compare it. So if you want, you can generate a factor of safety plot. Right clicking here and go to factor of safety plot. So I can right click and go to factor of safety plot. So when I go to factor of safety plot, it will ask me to select all the bodies we have or selected bodies. Here we have only one body, so I can have all the bodies here. Then criteria depends on the max 1 meter stress criteria. So I have to give that maximum 1 meter criteria. If you want, you can give upper limit for the factor of safety, or else go to the next option. So factor of safety is what are the conditions we can give now? Okay, so we normally we will calculate the stresses in megapascals. So keep this as it is. Then we can go to the next option. Here we can see factor of safety distribution, areas below factor of safety. So if you want, you can get the entire factor of safety plot, or else we can give a value like this. Give me the areas which is having less than 3 factor of safety. So in this example, what they have done is they have given 2. So they have given 2 as the limit. That is, software will only show me the areas less than 2. Actually, less than 1.5 are the worst cases. So 2 maybe. So he will show me only the areas which are having less than 2. So you can give that 2 here, no need to change anything here. Then here maximum 1 stress criteria. Press OK. Now it will show me the factor of safety plot. So these red areas are less than 2. So these areas are the areas which are highly there's a high probability of failing these areas. Blue areas are quite okay, they're higher than 2. So you can get the stress plot, or plot is also showing the same output. Factor of safety plot will quickly show me the areas which are critical in this analysis. So what I did was I right click and went to factor of safety, then select all the bodies, then went to the next air condition. So I will show you the inside edit definition. I gave the one misses criteria for all the bodies. Then I kept this one as it is. Limit, we are measuring the limit from yield strength. Then we gave less than. Any questions about this? Okay. Any questions about this plots? Now I said that don't believe this result. This is an approximation. This is not the final answer. So we have to do some optimization. So next we have to go through that area. So I hope you are okay up to this point. So now next thing is we need to fine tune our elements and see what are the results we are getting. So we have to do a remesh. So we are in the cost level detail. We can apply medium measures and we can apply fine measures and see whether the solutions are getting converged. So you have to check whether the values are getting converged to a certain value. So if it is not, then there will be problems. So we will look at that one now. Uh, Now this can be renamed as I will rename this one as a course level mesh study. You can right click and rename. Now I have to do a medium level and a fine level. So we cannot do this again and again. It's a waste of time. Only the mesh is changing. So other conditions are unchanged. So we can do what? We can do a duplicate. We will duplicate this existing course mesh and get a medium mesh. So I will rename this now. Medium. So I am getting a copy. So all the things will come, but not the results. So I have to get the material copied, fixtures copied, forces copied, and now the mesh I will change it. I will change the mesh to a force level mesh. So we will medium level mesh. So I will reset this into medium. Then the mesh parameters will be 5.7. Tolerance is increasing, and I will press OK now. Now you have a better mesh. So if you look at the details now earlier this was I think 98%. Now it's 99%, and you have a high quality mesh, and your nodes and elements have been changed. So if you just look at my slides, this is the course level details. So you got around 344 one misses value. When you apply medium level, the element size is 5.7, nodes 12,208. In my one, it's 12,208. Exactly that way. Then I have increased my nodes. Degree of freedom is increased. Then displacement value is also slightly changed, and the stress is going to change a little bit. So I will run the simulation and see. It will take some more time. And now this time it's increased to 200, 307. Now earlier it was 340. Now I have a problem. It has increased. When I fine tune my mesh, my results are getting more accurate. So my displacement is now 0.124. Earlier it was the same. So displacement we are getting 3 decimal places. If you try to get it for more than 3 decimal places, we will see there will be a change. So I will try to get more decimal places here. 5 decimal places. 0.12353. Now this is 0.12377. So slightly the displacement has been increased. See, since the displacement has been increased, stresses also has been increased. So now we have a problem. Whether I should believe this value or whether I should believe this value. So I can't believe any of these values at the moment. Okay. So you can run this and see whether you are getting a value closer to 370. Now we will do a fine mesh, further fine mesh. So I will duplicate this and apply a fine mesh. So other settings are unchanged. So I will put the slider to the right side, fine mesh. Parameters, now the element size is really small. Okay. Now you will see a very fine mesh in your computer. Lot of elements. Mesh results, details. You have now 83,796 nodes, elements 54,000. So in my slides also, it's somewhat closer to that one. Now, when you run the simulation, we will see what are the displacements and the stresses. It will take more time now. Now it says 377. Earlier it was 370. Now first one it's 343. So you can see that it's increased. It's increasing, but the increase now has been slightly reduced. If you plot it, it's something like this. It increases from 340 to 370, and when I fine tune the mesh, the slope is now reduced. That is, it's now trying to converge to a certain value. So you have to refine the mesh further and further and see what is the actual value. Actual means what is the converge value, final answer. So you can do these things and see. Any questions, let me know. Try to get the fine value which is closer to 377 and let me know. I will proceed. So you can see running simulation will take some time. Actually modeling is easier than this because we have to run several simulations and it will take some time. So don't keep the simulation till the end of the project. If you are doing a project, allocate some at least 40% of the time for the simulation. Lot of guys don't keep allocate time for the simulation and they are struggling when it comes to a deadline because this will take some time, and since this is a simple model, it will quickly generate the results. But if you are analyzing like a vehicle engine, it will take hours to generate the results. So don't keep the simulation things till the end of a project. Do it, have some time for this. Otherwise, sometimes the computer will crash. So a lot of problems comes when it comes to simulation. I said we have to do a fine tuning and we have to check whether this can be accepted or not. So we have to see whether the results are going to converge. That is, it should be a constant value when I increase the number of elements. Now we will apply one more mesh and see what happens. I hope you are okay up to this point. So if you look at the factor of safety this time, the last one more or less the same outcome is appeared. So I will take a copy again. Say I will do a say another further refine. So I actually in the slider I have gone to the rightmost end. But if you look at my this one, I am in the rightmost end. So I cannot go beyond this. But if you look at my parameters here, I can type a value here. So now 2.8 is the maximum value, minimum value I can have as an element size. So if you just try to type say like a 1, manually we can type a value. Automatically the tolerance will change. So I have given a value. This is from my experience, gut feeling. I gave a value called 1. So you can apply some value here and see whether the stressors are going to converge. So I will press OK. It will take some time now, and it will have a lot of elements this time. So see how it's taking time. So actually, should we waste this much of time for this kind of a model? So that's up to you to decide whether I'm going to satisfy with the previous results or should I invest time and money for this kind of a fine mesh. So that depends on the model you want to analyze and what are the how critical that component in your design. So it's all about making some decisions. So here I'm wasting a lot of time uh, for this kind of a simple mesh. So all depends on the computer also. If the computers are slow, simulation cannot be done. So actually I'm wasting my time here. So hope you have generated your mesh. So I will cancel this. So this is the problem when it comes to simulation. You have to have a lot of time allocated for the simulation when you do a project. Otherwise, you will be struggling with the deadlines. So I will not go for 1 millimeter. I will say 2 millimeters. So at 1.8 millimeters. and never run simulations in a pen drive. So better you do it in the hard disk. Otherwise, it will take a lot of time to transfer data between the pen drive and the external hard disk, or the pen drives and the computer. So never run simulations on pen drives. Uh, so now this is a very fine mesh. Do we need this kind of a fine out mesh? So if I just look at the details, elements now increase to 201, 210,000. So lot of elements. 99.9 is under 3. So when you run the results, uh, so I got the values. It said 378. Earlier it was earlier it was 377. So you can see the values are now converging. So 378, 77, those are quite acceptable. So I should not fine tune the mesh again, because 378, 77 is quite okay. So you can actually believe this value, 377, the earlier value, can be accepted. So don't accept the first one. First one is 343, which is wrong. 300, second one is 370, which may not be very accurate. These two are quite near to each other, close to each other. So 377, this is 378. So if you go with another finer mesh, this may go around 379, 380. So no point of going to another fine mesh. It will say waste your time and computer processing power. Processor. So we can rely on this 377 and accept this value. So that's how we conclude our simulation. So I hope you understand. So you have to do some refinings and try to get a converged plot. If it is going increasing and increasing and increasing without converging, there is a problem in your model. Probably you have to apply some fillets and reduce the stresses. Otherwise, it will climb without converging. So I hope you understood this simulation. Any questions about this? So we have to look at the mesh properties, see whether the aspect ratios are okay, whether the quality is good, whether there are considerable number of elements here, and do some run several simulations and see whether the stresses are going to converge. And we can get the factor of safety plot also. And these are the red areas, are the most critical areas. So here also I can see These are the critical areas. So you have to do some fine tuning in these areas to avoid permanent deformation. So we can't remove the load. Load is there. So load cannot be reduced. So we cannot change this fixture. If you want, you can apply some other fixtures and support. But if you cannot change the fixtures and the loads, only thing you can do is you can change the materials, or else you can change the geometry. Okay. You can apply some fillets and see whether the stresses are going to reduce. So those things can be applied, or else you can increase the thickness here a little bit. So that's up to the designer to decide. Any questions after this one? Okay, so we will now run another simulation. We will now repeat our analysis of the hollow plate by using prescribed displacement in place of a load. So what we are going to do is we are going to remove this 100,000 Newton, and we are going to apply a displacement and see whether we get the same results. So when we run the simulations, uh, when we run this one under medium conditions, we got a displacement value around 0.123. Or else if you look at the fine values, it's 0.123. So this displacement is obtained by the force of 100,000 newtons. But now in the example, they are trying to apply another. They are removing these forces and they are applying this displacement frequency. Whether we are getting the same output as the reaction force. So we are doing it in the other way and see whether we are getting the same outputs. So if you look at my computer results and the tables here, it's somewhat different. Here it says 0.118, but if I look at my computer, it says 0.123. So there's a difference between my values and the in the book value. So in the slides. So don't worry, we will use value coming here. So no problem with that. So I will use this static medium result, and we will duplicate this and create another one called static medium, say displacement. So I'm going to give a displacement as the input. So I hope you are following me. Earlier I gave forces. Now this time I will delete this force, or I can suppress this. You can suppress or delete. Without the force, I will give a displacement. So when you give a displacement, we can calculate the forces and see whether we are getting the force near to 100,000 newtons. So we will apply a force now, sorry, displacement to this space. So we can right click and apply a prescribed displacement. So earlier we applied a force, now this time we are applying a displacement. See, we will go to standard ones, sorry, advanced ones, and use this condition called on flat faces and apply a displacement to this face. So the displacement should be normal to the face. So this value should be turned on 0.1, sorry, 0.123 in my one. So I will do this again. So this is the maximum value I got, 0.0123. So I have applied that as the displacement value. So you can right click here, go to right click here, go to prescribe displacements. So when you go there, we are assuming this is a flat face. So I am selecting this on flat face condition. Then select this face, and I got a result of 0.123, and that is normal to the face. So what I'm going to do is without applying a force, I'm trying to applying a displacement and see whether we are getting that 100,000 force as the reaction. Okay, so this is in another way. So I have a criteria. This side should be fixed. This side I have to have maximum displacement of 0.123. So when I apply 0.123 displacement, what are the stresses? What are the reaction forces generating in this model? So you can model that way also. I don't need to give forces always. We can give displacement as the inputs. Okay. So I use this on flat faces. So the displacements can be in x and y direction also. So here it's normal to the face. So if you want, you can enable these things and give other values even. So that's not needed here. Only normal to face. I hope you follow me. Any questions, let me know. So in the book, they have given 0.118 because they got that result. So I got 123. That's why I gave 123. So if you get another value, say 125, you give that value as 125. So this direction should be changed. We will reverse the direction. So here I am assuming everywhere I am getting this same displacement. Earlier cases we didn't assume that. Earlier cases along the edge the displacement are different because this is not a uniform shape. There is a hole here. Because of this hole, the displacement of this area is different from displacement of this area. So earlier case the results are different. So I will press OK now. So if you look at our earlier case, static medium, displacement, this displacement is plotted like this. So along the face, it's going to change a little bit. We can't see that change greatly big, but there will be a change. So if you want to look at the change along this edge, there's a way of doing that. Now this is the earlier simulation. So if you want to look at the changes along the edge here, what we can do is we can right click on this and get this tool, list result force. So you click on this tool and not the force, this stress displacement strain. So you can click on that and go to displacement here and click on advanced not from this not from this you cannot take it. So remember that everywhere we don't find 0.123 here because there may be slight changes depending on the shape here. So this area may have maximum value. So 0.123 may be maximum here, not here. So remember that when you run the simulation. So we will look at the new model now, this one. So I have given this one as the input. So same mesh, we will run this and see. Now you are getting the same, almost same value, 372. So if you look at our earlier mesh, stress values are 370. So when I apply 100,000 newtons, I got 370. When I apply, when I apply 0.123 displacements, I got 372. So you can do in both ways. So that's what I want to tell you. You can apply a load or you can apply displacement and generate the stress values. So if you just look at the displacement plot, just say 0.123 everywhere. So I hope you understood what I did. So inputs can be given in different ways, either by forces or either by displacement. You can run it and see. Any questions, let me know. Now, if you want, you can calculate the reaction force now. Now we can right click on this results and there's a tool called list result force. So we can select this phase and calculate the reaction force here. So we can update this. You can see a table has been generated and you can see the resultant force is around 100,000 newtons. So the Fx value is in x direction, it's close to 100,000. So if you want, you can save it as a graph. So same results are almost coming. So when I give a displacement, the reaction forces here will be close to 100,000 newtons. So how did I get that? I right click on this and got the list result force. So you can select this phase and update. Sorry. You will see that value come. So you can do this simulation in different ways. One is you give the forces and calculate the displacement. So if you know the displacement, you can calculate the resultant forces, reaction forces. And if I'm going fast, let me know. So now there's another tool here called probe. Now when I right click on the displacement probe, if I click on this edge, you can see everywhere along this edge the value is 0.123, because I gave the displacement as 0.123. So I gave this as the input. So everywhere it should be 0.123. It's okay. But if you look at the stresses and go to probe along this edge, it's also same, because I gave the displacement. So when I gave the displacement, it will calculate the strain, and strain will be multiplied by Young's modulus. Then the stresses also is going to be same. So this is coming because I gave the displacement as an input. But if you go to our previous cases, medium case, and check the probe displacement, right click and get the probe along this edge. Is it changing? Now when I plot it, you see displacement, you can plot it. So you can see the displacements have been changed. So earlier in this graph it's only showing me, now if you look at this one, it says maximum is 0.123, but I don't know where the maximum is. So if you just edit definitions here and try to plot, get the maximum point, here we have the maximum is here. It should be right in the middle because of this shape. Okay, so if you want to get a plot along this edge, you can right click on this and go to probe and go to unselected entities and select this edge or the face and update. So you can see the plot. So along the edge, this is the, along the face, this is the result, but this is not really good. So we can select along an edge and update and plot it. So you can see the maximum displacement comes in the middle of the part. Why maximum displacement coming in the middle of the part is because of this hole. Here there is less strength, so there is a tendency of more displacement in this area because there is a hole in the middle, symmetrically in the middle. Okay, so this is the maximum value I am getting, 0.123717. So this is the minimum value, 0.120. Minimum value is, so from the color plot I can't see that. So better you generate a graph like this. So you can right click, go to probe, on selected entities and select this edge or this edge and update. It will generate the table. If you want, you can save it in the Excel format or else plot it. Also this plot can be saved as a picture or a CSV file or a picture. So I hope you understand. So when I apply 100,000 newtons, the maximum displacement is here. But if you look at the stresses here, we will probe it and see on selected entity along this edge, update and plot it. Stresses are acting like this. So stress is minimum here, maximum in this form. So that's what von Mises says. And if you look at our last model, I gave the inputs, displacement as the inputs, and get the plot here. Probe on selected entities. This one, update plot. It's a constant. Why it's a constant value is I gave the value as 0.123 everywhere. 0.123, 123, slightly changing depending on the numerical errors, but it's 0.12. So I hope you understood what I did. So we started with the coarse mesh, fine mesh, medium mesh, fine mesh. I further refined it, and I said that the stresses should converge. Then we can stop it somewhere here. So it was stopped somewhere in 377. No need to go to a fine one, further fine mesh. It is 378 only. It is not needed. Then I change my inputs. And put this as fixed geometry. It's not changed. Input was changed as the displacement. And I use the medium mesh properties. Medium mesh properties. So you can run this. Medium properties. Then we got the displacement values. So the displacement values are everywhere the same value. Stresses also everywhere it's same. So we then we calculate the reaction force from these these result forces, and you can calculate the reaction force along the edge of the face and update. This is the reaction force, which is equal to the almost equal to the 100,000 units. Any questions about this? So your results are saved in this folder. That is the folder I'm working. So if you want, you can save the results in the temporary location or whatever any other folder you like. So SolidWorks document folder, I am saving everything in that same folder results. So that's why I am getting lot of files in my folder. So if you just look at my folder, it's now filled with lot of files. Now if you want, you can generate a report from this. So there's a tool called report here. So I will generate a report of these things I did. So this is automatically generated report. I will click on that, and if you want, you can get all these things into the report and write the names and other things, and I will publish now. So this is the report software has generated for me. So all the things are nicely laid out. So the model information given, masses, volume, density, everything is given. Then the mesh details given. Sorry, after solver details, all these things given. Then units given. Then material properties. Then loading conditions, resultant forces, contact information, mesh properties, then resultant forces, plots. All the things are nicely plotted, and the most important thing is not given. So the conclusion is not given. So the computer cannot do that. So it's up to us to write a conclusion. This is the most difficult part in the simulation. So writing the conclusion will be the most difficult part. So you can use your engineering knowledge and write a conclusion why we are getting these kind of results. What are the why? What can we do to prevent these failures? So why we are getting these red areas, blue areas? So that's the most difficult part in the simulation uh, environment. So I hope you understood the concepts I did today. So any questions, let me know next day. So next day I will start analyzing L bracket, and I will look at more areas in static analysis. So next day also I will do some examples and show you how to use the software effectively. So we will finish for the for today's, and we will meet next day. So thank you for joining the